In this video, we'll take a look at an overview of the last section in Chapter 5. That's Section 5.7, and that is a change of variables theorem in multiple integrals. The idea behind this is the same thing that we've been doing already. When we change our variables x, y into r theta in polar coordinates, or we change our x, y, z to r theta z in cylindrical coordinates, or change our x, y, z into rho, phi, and theta in spherical coordinates. We kind of did those change in variables, and we produced this extra r in polar coordinates and also in cylindrical coordinates. In spherical coordinates, we produced this extra rho squared sine phi. And so we can use geometry. The book does geometry to compensate or to explain what those compensations are about. But if you truly look at the U substitution way of doing things, you're looking at a differential. You're looking at some derivatives that are involved in the changing of your variables. And so these derivatives can be seen more directly using the Jacobian. So the idea is that we're going from a rectangle to a stranger shape, and what we want to do is we want to describe that stranger shape as some sort of transformation. And then what we're interested in is to figure out okay, what do we need to compensate for these transformations? And we're essentially looking for the area using parallelograms. And the parallelograms that we're using are like the delta x and delta y is going to be some delta something and delta something else. That's going to give us the area of these little parallelograms that are approximates of these other, non-parallelogram shape things. And to do that, we're going to it's essentially a cross product, but we're talking about this in 2 dimensions. So the third component would just be 0, but it's essentially a cross product of 2 vectors that we're looking at. And those vectors can be, the crossing that we're going to be doing are going to be some partial derivatives. So this quantity is called the Jacobian. It's essentially the absolute value of the set of partial derivatives that are given here, and that's like your differential derivative that you compensate for when you change your variables. So when you do your double integral, you're going from r with a regular dx dy, and so that's this r over here, the first picture on the right side, and then you pull it back to S, where now S is a nice rectangular region. So that nice rectangular region will just leave you with constant limits if you were to continue on with a change. But then your compensation for the change is this Jacobian. So again, the Jacobian for spherical coordinates or polar coordinates is r. That's the stuff that's happening in 2 dimensions. And this is our example. Again, the R discussion that they gave in the textbook was all about geometry, but we can really take it up to calculus and figure that out. The same thing goes for a 3-dimensional transformation, where we get something that's difficult to look at in 3D, and then you kind of reshape it into a box so that you'll have nicer limits and nicer functions to deal with. And again, this would be like a linear combination of 3 vectors, or how our 3 tangent vectors would come back to our square or our rectangular coordinate system. And here we have the Jacobian now as a 3×3 matrix, a determinant of a 3×3 matrix. And in that determinant, we're going to come up with that differential factor that we're going to multiply by. So again, a flashback to cylindrical coordinates and spherical coordinates. those are obtained by doing this Jacobian, and in cylindrical coordinates we get an extra r, much like we did in polar, and in spherical coordinates we get that rho squared sine phi factor. So that turns out to be the Jacobian when you do your transformation from rectangular to spherical coordinates. All right, so that is our overview for the last section, and hopefully you got a good handle on double and triple integrals and the switching coordinates, and some physics applications with the mass, center of mass, and some moments and moments of inertia. And then finally we top it off with the change of variable to kind of recap the cylindrical and spherical coordinate and the polar coordinate changes that we did. This is more calculus justification for those transformations. All right, good luck.